Hello everybody, welcome back to our MSE 100 lectures. So we've been kind of like doing a lot of interesting stuff so far. We've been switching back and forth between SolidWorks and kind of creating hand drawing of stuff. So if you remember, we were looking at perspective views last, and then we were looking at creating 2D views of objects, right? So we were basically kind of trying to create what is called as a multi-view, as well as the isometric view of different 3D objects. So we did do some more interesting homework problems, and then we'll go back, kind of like loop around. So again, in this video, we are once again going to do two different aspects. So we'll focus mostly on SolidWorks, but at the same time, we kind of switch gears again and then start looking kind of at a similar problem to what we did in the homework. So with that, so let's look at our learning objectives and the topics for the day. So the learning objectives are going to be the introduction to assemblies in SolidWorks, and then we look at some additional practice on multi and isometric view, which would be in line with what you did in the assignment. So here is the introduction. So we'll do the introduction to assembly, talk about constraints, we'll do analysis of constraints, we'll talk about toolboxes that are available, and then we'll kind of switch gears back toward doing the hand drawing, where we kind of like review the edge numbering, and then we'll go at an optional additional assignment, more of a practice assignment. So an assembly is used to essentially globally link parts together. So we did look at a simple table, if you remember, but nonetheless, if you look at an actual table, it once again actually consists of a lot more parts, and essentially, similarly, any object you actually take is actually going to be an assembly of multiple parts, and then there's going to be a specific relation between. There are a lot of examples. So a simple example would be, if you take my pen, so this itself is an assembly over here. So if I was able to open it, assembly, so we have this threaded section over here, and then there is a spring, and then you have the ink, and then there is a, if you look closely inside, there is a little bit of a small ball inside this metal cylinder, and then the ink, you have to kind of like design all of this properly, kind of look at all the tolerances and so on to actually ensure that you can actually assemble them together. And then you can potentially use additional components over here. So this, if I put this back together, assuming I can put this back together, and then you want to basically make sure that, you know, like this one, based on how it's set up, you can kind of like click it and then close it, or some of them you have a clicker at the black, so you have to kind of, those have a CAM mechanism to them, and then you figure out how they actually are assembled together. Another example is, if you kind of look around, so hopefully you're in a room, not floating around or having fun. Maybe that'll also be nice. But nonetheless, if you do go back to your room, so you can take a look, so that the door that they have is kind of, again, a complicated assembly, right? So if you think about it, let's kind of think about what is going to be happening. So if you think about the door, so now would be a good time to pause the video and actually think about this, and then maybe kind of create a quick notes on what is involved and how many steps are involved here. So if you imagine, so the latch that they have, so for the door you have a latch which is actually going to connect the door onto the frame, and then the hinge itself is also going to be an assembly, and then when you put these together, all of these need to be assembled properly. So if you think about the structure itself, so essentially, if you have the door, you need to basically place the holes for the hinges exactly the same distance apart, and they all likely need the same size. So you can have like a 20mm hole on the wall, and then you try to put in like a 10mm. It's not going to really work. So all of these need to be designed together, and you need to be aware of what is the relation between them. So kind of just to illustrate, So this again is a kind of a photo of the IKEA assembly I found online. So this is the source that I got this from. So essentially this is kind of an IKEA hinge. So the hinge itself is again a more complicated assembly. So if you do have one lying around, you can kind of take it apart and then see how the whole thing is laid out. That's one aspect of it. And so that will become like a sub-assembly in your bigger assembly of your cabinet. And then if you think about it, so it's going to have two holes here. They need to be specific distance apart. So if they're 32 millimeters on the IKEA hinge, there's going to be 32 millimeters apart on the door as well. And then to actually assemble this part together, again, so that needs a specific kind of a diameter hole. And then you need to basically match the holes for the screws on. So you need to match the holes on the screw um, on the door here and here with the same distance between the holes on the um, essentially the hinge as well. So all of these need to be taken into account when you're kind of creating the whole assembly together. So this is going to be kind of look where you would look at the interrelation between these parts and then be making a consistent assembly. So when you're actually creating the assembly in SolidWorks, these are higher level thoughts that you would actually have, but to actually get the assembly to function within SolidWorks, you're going to be following a slightly different workflow within SolidWorks. So that's where we get into constraints. So to create assembly in SolidWorks, we are actually going to use constraints. The conceptually, excuse me, I can tell you that if I put a screw through a wood, it's going to hold the screw in place. Unfortunately, that is a lot of logic to actually program into SolidWorks, so it doesn't really know kind of like concepts of gravity, or you can set it up, but it just makes the whole calculation a lot more difficult. And then you can talk about like the clearances, whether or not it's going to fall out. You can kind of like program all of those together, but that would just make the program very, very complicated, and it doesn't really give you too much of a benefit. And more often than not, it could kind of like mess up and you wouldn't be able to create what you need to. So instead, what we have is we kind of like impose all of the constraints or we impose the effects of the constraints within the SolidWorks. So essentially, if I have an hinge, so I basically say I can kind of set up a constraint so that it kind of is always going to be rotating about the hinge point. If I have a door, I can set up the constraint so that if I kind of fix the hinge to the door, I can kind of virtually glue those parts together, or kind of like have another type of constraint which enables relative rotation or relative translation in one direction or the other to do more complicated set of limitations on the degrees of freedom, which is what the constraint actually does. So if you recall, this concept is very similar to what we did in terms of the sketching constraint. So we basically had, like, if you have two lines, so they could kind of like go relative to each other however they want. But if we basically fix those two points together, this second line is kind of like dependent on the end point of the first line, so it cannot arbitrarily move. So the concept of constraints within essentially within assemblies is very, very similar, and kind of like it just extends those things. So we'll start looking at the list of constraints. So I do have some free space. If you printed the notes out, we can use that space to kind of make additional notes when we actually switch to SolidWorks and actually kind of doing the discussion here. So the first constraint we're going to be looking at is for planar objects, or kind of like creating planar constraints on planar objects. So what do I mean by planar objects? So both of those sides are going to be flat, and then I'm going to look at how is it that you can basically set the constraints for those objects. So imagine I have these two planar objects over here. So essentially, if I bring this to closer, we can think about how we'd actually set these two surfaces, right? So this would be a planar surface and this would be another planar surface. So I can do multiple things. So I can make these two surfaces, so the ones I'm holding my fingers on, so I can make them parallel. So I can kind of like set the distances between them. I can actually make it parallel and on the same place, which would be coincidental constraint. So the two planes are located on the same location. I can also have them kind of like facing each other. So these are two ways I can actually set them together. So I can actually set them to be parallel, facing the same way, or we can have it facing towards each other. We can actually have it parallel and then kind of set a distance, either in kind of like facing the same direction or facing each other. And then we can make the two faces perpendicular. So where I have this face where I'm holding, and it's going to be perpendicular to the other face, or I can basically make these two faces at a particular angle. So these are the ones we can do. So we can actually, just to quickly note, we can actually make them coincidental or parallel constraints with either facing the normals facing each other or facing away from each other. SolidWorks has a specific terminology for this. So if we kind of like think about coloring those two faces, so SolidWorks basically calls if the normals facing the same way as a line, and then if the normals are facing in the opposite direction, we're going to call it as a mated constraint. So rather than just arbitrarily show you some diagrams, so we'll basically try to create a constraint, or actually the set up the constraint for the table case. So here is what we have. So we're going to have this particular table. So we look at the constraints, and then we look at the table constraints over here when I open SolidWorks over here. So here we are in SolidWorks. I'm going to create here, click on new, and then click on part. And so we're just going to do the first very simple example. So where I'm going to just get two different planar surfaces like this, and then kind of like look at the different ways I can constrain them. So let's maybe just click on the front plane and then create an arbitrary rectangle here, mark dimension. So right now I think my units are in meters, so I can change that. So one, I go back, I can actually, if I had the units differently, I can kind of go back and change it to millimeters. And then we kind of edit the sketch, mark dimension, so we can fit maybe twice or three times. Exit. Then we're going to sketch. So we're going to extrude this. So let's say by 10 millimeters. So it's already 10. So we're going to say OK. So now we have one object. So let's save this. So I'm a little bit lazy. So what I can do is really quickly, I can just save this as another part. So I'm going to do control. So control shift S doesn't really work. So I'm going to do file save as, and then maybe we'll just call this part B over here. So right now I have two parts, and just to illustrate what's happening, so I'm going to select this face and then change the color setting. So click on appearance, and then I'm going to click on the face, and let's pick two colors. So I'm going to do maybe blue and orange. So blue, A, save this. And this is the other part that we previously created, and then we're going to basically change the appearance over here. Then we'll change this to say a different color. For instance, orange is going to be yellowish right here, and then we say okay. We'll save this part as well. So now we are going to create our new assembly, and it's not super difficult. So what we do is Control N, And instead of clicking on parts, we're going to click on assembly over here, and then we say okay. So once we have this, since I have my V05A and B open, it's actually showing those as the open documents. If I didn't have those, I can actually browse and then select from what's available in my desktop. So here I'm just going to select part A and kind of like place it arbitrarily here. And once we do this, we can kind of like go back to the assembly over here. So click on insert component. And since this is open, you kind of like click on this and then say, okay, place this here as well. So we can save this. So you'll notice that I can actually grab hold of this part and then move it anywhere I want because it's not really constrained. If I try to do this with the first part, it doesn't seem to kind of like move anywhere, right? Hopefully everybody notices that I'm kind of like grabbing hold of the mouse a bit. I'm not strong enough, but this one seems to be moving, right? So let's see what happens here. So if I go back and look at my drawing over here, let me just here. So this is kind of like a zoom view over here. So you'll notice this actually has an F on here. So this one doesn't have an F to it. So the reason this has an F is because it's actually frozen in space. So the way SolidWorks actually works is the first object that you place gets automatically frozen in place. So we didn't actually want that. So what I can actually do is right click and I can actually kind of like say float. And notice that now this has basically become a dash, and which basically indicates that the object is actually free to move any which way it actually wants. So I can actually move, right click and say fix, and then which basically fixes the first object. If I right click and say fix on the second object over here, it kind of like fixes the second object, so I can't actually move that anywhere I want. So this is kind of fairly useful because generally the first object that you place, you don't want all of the objects to be moving all over the place. So it's generally a good idea to fix at least one of the objects. And it's usually not a great idea to fix all of your objects in your assembly because eventually you want to assemble or mate these together. So let's float the second object and then now you can actually move it together. So what SolidWorks also does is it assumes that the lowest object is kind of like placed on the floor, and based on the lighting, you can see the shadow actually changes, which is kind of a cool feature to kind of like visualize what's actually happening. Also to get a sense of how far the object is from ground. So let's come back. So I'm going to want to mate the surfaces. There are a couple of ways you can do it. You can click on the mate menu option, or you can select these two faces and then wait for this context menu to actually pop up. So here it gives me the different options. So coincidental, parallel, perpendicular. So let's click on coincidental. So now based on how I actually place the object, these two faces have merged together. So if I wanted to change, I can right click on my mates over here, and then it shows a drop down menu. And then if I say edit feature, I can actually change the direction of mate. So here these are aligned, basically kind of like pointing towards us in the same direction, or towards you if you're watching the video. So what I can actually do is kind of like flip these. And so then now if you note, and then I say okay, so notice that the orange face is facing me and then the blue face is facing the other direction. I'm actually using my middle mouse key to actually rotate the object or rotate the view. So let's go back, Control 7, and Control 1 gives you kind of the front view. Then if you want, you can kind of like fiddle around with this view. This is what we get. And now to illustrate that the mate is actually set properly, it is like facing each other like so. So if I kind of try to pull on this object, so you notice that it does appear to separate, but you need to rotate to this view. It's going to be like control 3 left, or I can go control 4 in the right view. So now if I try to pull the objects apart, they don't seem to move at all. But nonetheless, I can actually move second object relative to the first object up and down, and as well as if I rotate it like so, and I can kind of like move it same face as well. So that basically means it's kind of like sliding all over the place, but it's still kind of facing each other and it's mated on that face. We wanted to get an additional constraint, so we can look at the other constraint. So now I don't like these two being at an angle, so I can click on these, and then I can either make them parallel or make it parallel at a distance. So now it's picked up some value. So my assembly is also in meters, so I can actually change that 0.02, and we can change this to millimeters over here. So now if I go, and so you'll notice that this is 20 millimeters. So remember we made this 30, so about 2/3 of the way. So now I can't move this up or down. The only thing I can do is slide it. And because it's set, I can't actually rotate the object any which way I want. Here, if I wanted to rotate, I can have to click and then click on the rotate object, which will allow me to move and also rotate the object if I need it. We have these two. Now let's actually say, kind of this and this part, and then the only thing left to do is kind of make it coincidental, and this moves the object, and then now everything is kind of like stuck together, and then everything is perfectly assembled the way you want. So let's look at our table assembly. So we kind of have two parts which we can use as our legs. So what we need to do is actually create a part which we can actually use as the top of the table. So for that, I'm just going to do Control N, click on part, and because I made a mistake in setting up the units, I'm going to change this to millimeters over here. Click on the top view, new sketch, set this. So notice that it gives me the X and Y position, so I'm going to make it close to about 100, and then we can do the smart dimension over here, make this 100 millimeters and make this 100 millimeters. Okay, and we save this. And let's do control. I know I haven't actually extruded the table as yet, but nonetheless, let's see what happens if we try to import the part as is inside our assembly. So I'm going to click on new assembly, and I'm going to click on part C and insert it over here. So obviously this just looks like a sketch. The reason being I didn't actually extrude the part out. So let's actually save this and kind of like scratch our head a bit and try to figure out how we can get around this little mini conundrum or mini problem. So what I can actually do here is actually, if I made this mistake, I can right click and then I can click open part, which is going to kind of like open the original part. So let's switch back and see if we can do another way. So I'm going to hit Control. I'm actually been holding Control for a while. So if I now hit Control Tab, it's giving me the option to switch between multiple assemblies. I'm going to switch back to my assembly. So if I just hit Control Tab, it's going to go back to the previous windows. Control Tab. So we have here. So here we notice this is actually the assembly that we have open. So what I can do is also right click. And if I didn't actually want to open the whole part, I can right click. And I can actually click on where it says edit part. So what it does here is it's actually opening the part within the context of the assembly. So I have this option here, edit part, and then I have all of my other familiar menu options kind of just switched out a little bit. So here, this might be useful. So where it says whether or not you want to get external references. So this might be useful when you want to get references used in an assembly to be used in constructing the sketch or constructing the part itself. So right now I'm going to maybe just click no external assembly, click on my sketch, and then I'm going to click extrude. So this is extruding it to by 10 millimeters, and then I say OK. And we are basically going to click on this edit part again, which closes the assembly. Or closes the part and goes back to the assembly. So now I say save all. So now keep in mind that this is the first part I imported. So I can't actually move this part anywhere. So it's kind of like been fixed in place. And again, this has an F, which basically indicates it's fixed. So we're going to insert component here. So both of these are the same leg. So I'm going to pick leg A. I know it's a little bit of a short leg, but that's okay. So again, once again, I can click this guy and this guy. And then I can make it, so click on, so since I moved my mouse, I lost context menu. That's okay. So I can click on this and click. It automatically makes it coincidental. And then we say okay. I'm going to say okay just to show what we have here. So I can basically make and then still move this part. So I can actually list my constraints over here. So I can click and it says I'm basically made these two faces coincidental. So I can actually check that by rotating my part. So I click on part here, and within move component I have rotate. So here it has free drag, and where I can kind of like rotate the part like so, and then say okay. So what I can also do is kind of click on this face and this face and make it perpendicular, which will kind of change the orientation. So it turns out this is still perpendicular, so this wasn't very useful of a constraint. So I'm going to delete it. So here what I can do is kind of like click on the top and then the bottom over here, and then mate, select mated constraint. So this is actually coincidental, and then they're mated. So if I flip, my table is going to have a leg protruding out, which I don't want. Flip it again. Now it's assembled properly. Say OK. So for the most part, the table is done. I can just select this face and this face, and then it automatically inserts a coincidental constraint. Then we say OK. As usual, we save our part. And suddenly, if I realize that maybe I wanted this leg to be just maybe offset inside a bit, so what I can actually do is kind of, so if this menu is collapsed, I can click. Then as I move through, it tells me which constraints are highlighted. So I can maybe select this constraint and then say edit feature. And instead of it being coincidental, so I can actually make it parallel at a particular distance. So I click on this distance feature and then just maybe increase it. So now it's come out. So I can move in the other direction if I want by flipping direction, so where part actually moves, the leg moves into the part. So I probably don't want that. So I can go back and then just make it coincidental. And then make it coincidental. So where I basically change the constraint here. So once again, we save our little coffee table. So what I do next is, obviously I don't want one leg for my table, right? So I probably want 4 legs. So if you remember, if you're making this part, or if you consider making this part, you would basically make 4 legs, but all those 4 legs are going to be the same identical part, right? You don't necessarily need, unless there is a specific reason, you don't necessarily make completely different parts for each leg. So what I would do here is I can do one of 2 things. So I can either insert component, then click on my part A again and then keep inserting it. Or the other option is I can actually copy my parts with mate, or I can do more interesting stuff as creating a linear pattern. So the linear pattern is probably fairly straightforward, but we look at actually copying this with mates. So we right click, and if we go through these menus, just before delete, so we have copy with mates. So notice that it's asking me to select the component here. So this would be useful if I hadn't already selected the components before hitting copy with mate. So you can also get to the copy with mate from the menu option. In this case, this would be empty, where you would actually select one or two. So let's move forward. And so now it's already copied with mates, and then it's looking to paste all of these objects, or basically paste this leg in multiple locations within my assembly. So I can go through this. So I'm going to want to place one leg over here. So let's maybe make the top repeated. So that means it's assembled, mated here and here. And I'll maybe repeat this mate as well. So my leg is at the same location. So now here, instead of mating with that face, so what I can do is maybe flip directions and then select this face. So then it's put it there. So unfortunately, I can kind of like still fiddle around with these mates to try to get it aligned exactly. But I found that it's often more effort to kind of like fiddle around exactly with copy with mates. So what I usually try to do is copy with mates maybe like 3 or 4 or most of the constraint. And then if I notice that I'm just going in circles, so this, I notice that it's not aligned properly. So maybe I can kind of like disable this and then try to flip it. But then I'll notice that I'll just keep going in circles. So which I don't want to do. So I'm just going to say OK here. Then say OK. And then it's kind of going back. So maybe not repeat this. Repeat this. Maybe let's try repeating this. Far corner over here. And then instead of this, maybe I can select this face. So the thing gets flipped over. So let's say if I flip it, it looks at least close enough in the position, but not exactly. I'm going to call it for now and then come back and fix my edits. Then I'm going to say OK and then get the fourth one. So I'm going to repeat this. And let's say, so I don't want this face. Select this face. So probably not that either. For this face, instead of this back face, I'm going to select this face. And for this face, select the back face. So this seems to have assembled reasonably well. So I'm just going to say OK. And then now I don't want any more of these. So I'm just going to hit the X mark or cancel. So now I have a couple of legs which are outside my table, which is not that great for the stability. So if I drop down, there seem to be too many menu or too many mates here, which is a little bit confusing. So since I now only want to edit this object, so I'm going to click on that object and it gets highlighted here, and we drop down and then we're going to click on the mates and then try to identify which is going to be the problematic mate. So this one looks good. Maybe the top one, this mate, the top mate, so which looks good. So the second mate over here, this looks good. The third mate, I probably don't want that, so I'm just going to delete this one and then just select this face, control and select the other face and then make it coincidentally. So now it moves my leg inside. So we'll do the same thing for the fourth leg over here. So I don't know which one it is, but I click on it, it gets highlighted. Drop down, double check, and we go to mates. Let's look at the problematic mate again. This one looks okay. This one looks okay. This one not so much, so we'll delete this. Then select this face with the other face and make it coincidental, and which basically completes my table or the leg. Let's do Control 7 and again save the part. And this basically completes our leg assembly, and which kind of illustrates the different mates you can actually do here. So we didn't actually show you the angles here, but nonetheless, those options are actually available. If you actually click on edit feature, so you notice that all of the other angles, like the other mates, like the angle, the distances, and all of these are actually available here. So I'm not going to explicitly go over those here. So let's look at the next option over here, which is basically the central constraint. So this is basically cylindricity or concentricity constraint. So this is generally going to be used when you have two cylindrical parts. So either you have two holes that you want to align, or you have a cylinder with kind of a hole that you want to align. So for instance, if you have the engine block that you might make, then you have the cylinder. So you would want to basically make sure that at least in your assembly, so you would want to make sure that the cylinder is concentric with the engine block. So that's where we would use the cylindricity constraint. So let's take a look at this. So we'll switch back to our SolidWorks over here. So here we go. So here we go. So let's save this again and Control N. So here I'm going to create a part with a hole that will be used. So on the top plane, we create a sketch. And we'll edit the size of the sketch. $25mm seems like a good number. Okay. Because it's just a circle. So I can extrude it a little bit bigger, say 50mm. And save this. Call the 0 to A. So I'm going to be a little bit lazy and then hit File Save As here. And then we'll call this maybe B. So what I'm going to do is kind of like edit my sketch. And I'm going to create essentially kind of a rectangular box around this here. Dimension. Maybe you make this 50-50. So we'll exit the sketch and then see how it exactly looks. So notice that it kind of noticed an envelope and a circular feature in the middle, and then assume that is going to be a hole, which is good, exactly what we need. The only thing is I don't quite have it set the way I want it. So the hole isn't right in the middle. So there are actually multiple ways you can do this. So one way to do it is to create construction lines. So let's kind of look at midpoint here, point of the other line. And what I'm going to do is make this into a construction line. Then we select this point, then this middle point, and then we can make this kind of like a midpoint constraint. So what this has done is I'm basically using kind of another fictitious line to enable my constraint. And then now if I say okay, so now the hole is exactly in the middle. That's exactly what I want. We'll save this. So now we have V052 A and B. So one is a cylinder, the other one is kind of the maybe if you're thinking about an engine block, so you can think of this as kind of like a simplified engine block. So we'll do this, click assembly, then we'll save this. So because I have these two A and B open, we'll click on this guy, say okay, and we're going to insert. And so since we close the component, we have to browse and go here, and then we select 0 to A. Which is my cylinder. So now if I select the cylinder and the cylindrical hole and then click on mate, so it's automatically making it concentric. So it's going to assume that typically you would want them to be concentric. So you can actually make a touch constraint as well, which kind of makes it on the outside. So we can flip direction where it becomes tangential on the inside. The touch constraint is usually, it's going to involve more computation. So if it's going to be concentric, I would rather make it actually concentric. So and then we say A here. So now what can the cylinder do? So obviously this is kind of like transitioning like you would transition your engine inside the piston inside the cylinder. And so what you can actually do is if you wanted to make another constraint between top two faces, so again mate, then we can give a particular distance. So now it made it coincidental. Maybe I wanted it at a particular distance, and then I just say okay, and now it fixes it at that particular distance. For the circular object, so I can still rotate this face, which is not very evident from this particular view, but I can still rotate it because I haven't actually constrained it for the rotation axis, which you can if you really want it. So just to illustrate what we did, or kind of like recap what we did, so we basically took two cylindrical objects and then we discussed about how we create essentially like a concentric constraint, which will basically put the circular peg or the piston inside the cylinder or cylindrical block. So we'll switch back and then look at the other constraint that we have, which is going to be the touch or the tangential constraint, which is actually a slightly more advanced constraint between objects. So you can actually have it constrained like that between two cylindrical surfaces, or you can basically have a constraint basically like a flat surface and a cylinder, or basically between two arbitrary curves where you can basically do a touch or a tangential constraint. So let's switch back to our SolidWorks over here. So I'm going to keep this part that I have and then maybe insert another copy of my piston over here. Not an engine block. Now, and then we select. And so what I can actually do is take this surface and this surface and wait for the mate. If it didn't show up, we can do this. So now it's going to assume that it's actually going to be a concentric constraint. So now the cylinder has actually gone inside, right? Face I selected. So I can actually flip direction, which will bring my cylinder on the outside. And then I say, okay. So now the cylinder can actually move on the surface of the object. So this is not very useful for this very simple example, but you can use it for more complicated constraints. So this is what we did, and then we set up the concentric, tangential or touch constraints over here. So there is a reason I basically labeled it as one-to-one constraint in the previous when I talked about the central constraint and then the tangential constraint here. The reason is you basically have additional more advanced mates that you can actually do. So mates, kind of like get the standard mates here, and then you also have advanced mates, basically profile center, symmetric with constraint, which will basically be kind of like between two centers, or we can do like a path mate, linear coupler, and kind of do kind of like a distance or an angle over here. So there is actually like even more advanced or mechanical mates here, which is cam, slot, hinge, gear, rack, and pinion. So we'll kind of look at these two later on when we're basically doing toolboxes where we can get two gears and see how they actually assemble together. But for now, the rest of it, I leave it up to you to kind of like explore and just like play around and then see how it actually looks. So moving on, so here we talked about the tangential and touch constraint. So next, what we'll do is kind of like do some analysis on the number of degrees of freedom for each body. So generally, if you think about the 3D shape, how many degrees of freedom do you think it has? So now would be a good time to pause the video and answer the question. So if I have a 3D object here, so what it does have is it has 3 degrees of freedom in the translational direction. So you have 1, 2, and then kind of like move into the plane. So that's 3. The holy count here. What it can also do is it can kind of like rotate about the vertical axis, this axis, and about this axis. So in aeronautical terms, so this is known as a pitch, it's known as a roll, it's known as a yaw. So you can basically think about the pitch, roll, and the yaw axis, or you can basically think about the rotation about the 3 x, y, z coordinate axis. So again, so it has 3 translations and then 3 rotations. So basically, totally 6 degrees of freedom. So let's note that down. So we want to constrain all of these. What I need to do is actually I need to restrict all of these. So if I wanted to basically make sure that the object is fully fixed, other than fixing it to the frame, which I can do for the first object, what I need to do is basically make sure that I have enough mates so that the object is fixed if I need to, or if I'm basically designing, say, a cylinder and a piston, then I want to basically have the translational axis to be free. So again, so that allows you to calculate how many degrees of or how many mates you would actually need. The only challenge, or so let's note that down. So the first object gets fixed to the frame. So the rest of it, we physically think about moving the object, and then we see how many constraints we would need. So here things get a little bit more dicey. So there isn't really an easy one-to-one correspondence for the mates because we're actually in 3D. So I know what I said is a little bit confusing. So let's kind of like look at how many degrees of freedom each type of constraint takes away. So let's look at the first constraint. So essentially we have parallel constraint. So if I make, say, this surface, the front surface to be parallel, so it doesn't just take away one constraint. So it just, I do realize it can no longer move in this direction. It takes away one constraint for sure. But what it also does is if I make these two surfaces parallel, I can no longer rotate it about this direction either. So it actually takes away more constraint, and then I can not rotate it about this axis either. So if I kind of like try to do this, it takes away more constraint. So a parallel constraint actually takes away 3 degrees of freedom, right? So however, here's where things get a little bit interesting. So if I do 2 parallel constraints, it doesn't take away 6 degrees of freedom. So we do realize it takes away 3 degrees of freedom, right? So this object has 6 degrees of freedom. If I do parallel constraint, what it can now do is only thing it can do is slide up and down, or kind of like this is restricted, but I can slide this way. So it is basically restricted with 2 and then a 3rd degree of an in-plane rotation. So it basically still has 3 degrees of freedom. So just to illustrate, let's hold the cube in this format, and then let's apply a second parallel constraint between this face and this face. So what it does, or it basically makes the object like so, but I can still move the object this direction. So the reason this is happening is these 2 sets of parallel constraint tend to take away some, they have some overlap between the number of constraints they actually take. So in aspect, we need to be a little bit careful when we set up the full constraint, in that we might think we have set up all the constraints needed, but it might still leave 1 or 2 freedom which are still easier to, or which are still active. So let's note that down. So essentially, one parallel constraint, again to recap, takes away 3 degrees of freedom. This face and this face is being made parallel. I cannot move it out of the place, so it takes away 1. What I cannot also do is rotate it in this direction and rotate it in this direction. So it takes away 3 degrees of freedom, and then I'm left with 1, 2, and then an in-plane third rotation. So if I do two parallel constraints, so one parallel here, I can still move it in kind of like in that other direction, so it doesn't completely take away 6 degrees of freedom. It only takes away 5. So we need to be a little bit careful here. So if we look at concentricity, so it takes away 4 degrees of freedom. So the reason is, if I basically make kind of my hole, this is a cylinder. So what I'm taking away is I'm taking away the 2 translational, so that's 2, and then I'm taking away this rotation and then this rotation. So I'm actually taking away 4 degrees of freedom. So what the object can do is, if it's a piston and cylinder, it can actually move in and out, and then it can also rotate in this axis. This rotation we are not super concerned, but we are concerned about this kind of translation. And then if you're designing a cylinder and piston, you want to keep that translation. But if you're designing, say, a screw which goes into a hole, you probably want to take away that degree of freedom as well. So again, it depends on your application as to which degrees of freedom would be taken away. So let's move on. So the next topic we're going to be looking at is basically toolboxes within SolidWorks. So these are the steps you basically do. So you'll click on the design library, which is kind of located on the side, and then toolboxes, then add now, and then we're going to select ANSI, inches or metric, and then we'll select hex and all of those options. So let's look at how that actually works. So let me bring up SolidWorks. So let's do a new assembly to show how these actually work. Click an assembly. And what I'm going to do is I'm not actually going to import any of these. So I'm going to just say OK. And then now I have a blank canvas or a blank assembly over here. So let's see what else. So let's come back here. And what I'm going to do is click first one. If I move my mouse, it should give me a hint. It doesn't, but that's okay. We'll click on the next one, which is the design library. And we're going to click on the toolbox. And then I'm going to click on add now, which basically loads the toolbox into memory. So once I have that, I'm going to select one of these options. So we are going to select, so technically Canadian standard would be CISC, but you might end up working often the company which has close economic ties with the US, in which case you might end up using the ANSI inch or the ANSI metric. So I'm going to just show you what is available in these options. So we'll do the ANSI metric and see what shows up. So double click and open. So here you have the nut, the power transmission, and all of these options. So these are the different components you would use. So bearings are actually used kind of if you have relative circular motion between objects. So we are going to basically look at power transmission, just one of it. So the screws and bolts are obviously used to secure components together, and then the power transmission has gears and all of those stuff. So the reason there is actually a separate toolbox is these are actually going to be standardized components. So let's look at one of these. So if I look, I'm going to pick what's known as a spur gear, which is the simpler of the gears. So the helical gear is a little bit more complicated. It just makes it's used for more smoother drive. But now we're just going to look at the spur gear. So I'm going to drag and drop it into my assembly, and then when I do that, as soon as everything updates, it's going to give me a menu option here. So here I have different properties. So here I have something called as a module, the number of teeth, pressure angle, face width. So let's maybe just quickly go over one at a time. So the module kind of refers to the quote unquote size of the gear. So these are standard numbers. So the module is basically the metric module of the gear. So I'm going to select a size. So this is going to be determining the size of the teeth. So if I select, so right now it's 0.25 because we are in metric. This is going to be millimeters. So let's maybe go to 5, which will make it kind of like a quote unquote 5mm teeth. That's not exactly true. There is a standard notation for doing the calculation, which I'm not going to go. So the next one is the number of teeth, which tells you how many teeth are there. So right now it has 10 teeth. So let's make it maybe 20 teeth. So notice that the size of the gear teeth is constant. So if I increase the number of teeth, the gear just becomes a little bit larger. So here we have hub style. So this is, if you wanted to have a hub, it's kind of like a protrusion, like so. So here maybe I don't want the hub. And we have shaft diameter, so maybe make it a little bit larger, 10mm, maybe larger, 20mm over here. So that is the hole in the middle. So you can have keyways. Actually see it. Then this is the gear, and then it allows me to paste more of these gears. So if I realize I didn't quite do all of my edits, I can actually right click and say edit component part. Not actually, I don't want to click edit part either. So I want to basically say edit toolbox component. So this is referring to the face width, which is how wide this is. So generally, it's kind of like a function of the module. So I think it's automatically updated. It's generally about 1.2 times the, yeah, so it's probably not updated. So we can change the size if you want. And number of teeth to show. So what this means is if you wanted to have a basically like improve the rendering speed, so I can basically say don't show me all the 20 teeth, maybe just show me 3 teeth. And then what it'll do is it'll basically just show you the 3 teeth just for illustration purposes, and the rest of it is just blank. So here if I make it 20 again, basically shows all of the teeth. I can give some comments and then name of the configuration and so on. And I say okay again, and then this is the gear I have. So remember the component or the assembly that we had. Just for the fun of it, I'm going to import shaft. I'm going to think of my a piston as my shaft. So let's do insert component, and this is not what I wanted. So let's say if I can actually, instead of this, I can actually insert new assembly as well. So since we already have one assembly saved, oops, I'm going to say insert assembly, insert component, and then assembly. And just to show you that this is possible, let's save this first. I can import it. Insert component. So the gear is fixed. So I probably want to float the gear just for the fun of it, and make this guy fixed. And now I can actually mate this cylinder over here. I'll select those two faces and mate. So it's mated concentric. Okay. Then we select this face and this face, and it's made it coin. So I suddenly realized maybe the gear doesn't quite fit. So what I can actually do is either make my shaft a little bit smaller, or I can edit my gear and make the shaft, the hole in the gear, a little bit larger. Say okay. And then because of the way the assembly is set up, so this I can't actually move it from this part. But if I actually open the assembly here, edit the assembly, so now I actually can move. Actually, we have a mating constraint there, right? So if I basically change that mate distance, actually going deeper and deeper into the rabbit hole, change this distance is 1. So notice that it hasn't quite updated this assembly as yet. I need to just kind of like go through the mode, select OK, and then kind of like exit again. And then if it still doesn't do it, I need to rebuild the model. And the way I would do it is hit Control V, just rebuilding the model, and then it updates all of the assembly based on the constraints and other things. So I can still rotate the gear. So the way I would do it is basically click on rotate component, then kind of rotate the gear over here. So what I can actually do is I can insert another gear. For gear, and basically select, it basically did the same module and stuff, which is good. Then I can hit escape a couple of times, and I can make this face and this face coincidental. And so what I can actually do is I can do all of the other mates that we need, but I'm going to show you an advanced gear mate that you can actually do. Go to advanced, so you can actually, mechanical mate, and then you have an option of gear mate. So here, what we need to do is select 2 cylindrical surfaces which are going to serve as the references for the cylindrical faces for the object. So we have these 2, and then I can set up the gear ratio as some number between them. So if I do 1:1, this is not going to actually be great, because if I rotate this once, I'm going to rotate that a little bit more. So what I would actually want to do is basically set, based on the number of teeth here, I can kind of like set ratio so that if one rotates, count the number of teeth here. This is 20, and I think this is 12, and then you can kind of get, so if I say 12:20, 20 teeth, so then the gear mate seems to be working a lot better. So again, so you can play around with these to get more advanced features and look at all of the other mates that are actually available here. So this basically concludes the assemblies in SolidWorks. This kind of gives you the toolboxes and so on. And then what we're going to be doing next is kind of switching gears and then kind of like trying to do a problem which is very similar to what we did in the assignment. So for that, we'll kind of quickly recap the way that we created the edges, and then we'll proceed from there. So this basically concludes the assemblies in SolidWorks. This kind of gives you the toolboxes and so on. And then what we're going to be doing next is kind of switching gears and then kind of like trying to do a problem which is very similar to what we did in the assignment.